Hi, welcome back. So last time we talked about what it means to be a variable, right? A variable is just a characteristic about individuals or cases that you're interested in. And there's two types of variables. We said numerical and categorical. Another name for numerical variable is quantitative. Another word for a categorical variable would be qualitative. An example of a quantitative variable is the age. So maybe you're interested in the age of individuals in your population. An example of a categorical or qualitative variable would be like what county do they live in, or what type of shoe are they wearing. That would be a good example of a categorical variable. Now, when it comes to numerical variables, there are ways that we can take a look at all of the outcomes and find out what's the probability that you will observe those outcomes. That's called a probability distribution. A probability distribution tells us two things. What values did we observe? So if we're looking at the age, we can list all of the ages that we observed. And then we want to see what's the corresponding probability that you would observe that age. But since we have the population, we can go ahead and do that. We did that last time by looking at the total number of possible outcomes. So you just add up all of the outcomes and then take that value and divide it by the individual outcome for each outcome within your discrete probability distribution. And if you want more details on that, you can take a look at the previous video where I did an example of how to find discrete probability distributions using StatCrunch. Today we're going to make the transition into continuous probability distributions. And continuous probability distributions means that there is an infinite number of possible outcomes. You can measure it with infinite amount of precision. Another name for a continuous variable or continuous characteristic would be things that are measurable, like height and weight and blood pressure, right? I don't know if you remember, but unlike things that are continuous, last time we talked about things that are discrete, those are countable. And you can't measure those with infinite precision. The only possibilities are values like 0, 1, 2, 3. In the previous video, we looked at like the number of TVs that a house has. And that would be like some houses have 0 TVs, some have 1, so on and so forth. But today we want to look at continuous random variables. Let's take a look at this example on the screen. See what we got. In a recent study on world happiness, participants were asked to evaluate their current lives on a scale from 0 to 10, where 0 represents the worst possible life, 10 represents the best possible life. The responses had a normal distribution. When we talk about continuous distributions, things that are measurable, the most interesting, the one that we need to pay most attention to, is the normal distribution, which is a type of continuous distributions. In this case, we have a normal distribution with a mean of 6.3 and a standard deviation of 2.6. So in this case, I'm imagining that they're assuming that we have a continuous random variable, because somebody could say that, I don't know, from a scale from 0 to 10, my life's probably like, 7.5. Somebody could answer that. There's nothing keeping anyone from answering like that, right? So we have a continuous variable here. All right, and since they said it's normal, our probability distribution, our probability will be on the y-axis. Our outcomes will be on the x-axis. They range from 0 to 10. And they said that the highest probability, it has a normal distribution, so it has this bell curve to it. Okay, sorry, I didn't draw that very well, but I think I can recover. The highest probability on the bell curve is going to be right at the mean. What do they say the mean is? The mean is 6.3. Okay, and then a typical deviation, I'm sorry I didn't draw that very well. Maybe I just need to redraw it. Instead of keep on apologizing, I just need to redraw this thing. Okay, at 6.3, it has the highest probability. Okay, and then it says that the mean we notate with the Greek letter mu. This is the Greek letter mu. Usually when we talk about a population, comes from the entire population, we notate it with Greek letters. Okay, so the mu is the mean mu, mean. And the standard deviation also gets a Greek letter, sigma. Sigma standard deviation was 2.6. Okay, and then they want to know what's the probability, so this shows all possible outcomes, right? What's the probability that, here's the question, what's the probability that an individual, what's this? Find the probability that a randomly selected study participant response is less than 4. Okay, well look where 4 is. 4 is below average, so maybe like somewhere like right there. And they want to know the probability that it's less than 4, so that's to the left. I'll go ahead and shade that in. Probability that an individual is less than 4 for their response. Okay? Now, one of the ways that we could do this is we could convert this over to a standard normal, and a standard normal takes this and allows us to use the standard normal table. And it also allows us to compare the probability distribution with other probability distributions if we make it in a standardized measurement, right? So if we wanted to, we could convert this to a standard normal by looking at another normal curve. So this one's a little bit smaller, but I wanted to show you a standard normal. The standard normal always has a mean of 0 and a standard deviation of 1. That's what makes it the standard normal. Okay, so if we can convert these values over to the standard normal, we say, well, okay, we're going to convert our mean to a mean of 0, our standard deviation to a standard deviation of 1, and then we convert the individual value. The individual value in this case is the score of 4. We're going to convert that over to something called a z-score. And a z-score is just an individual value that will be placed on the standard normal curve. And how you find the z-score is you compare the individual's deviation from the mean, compare that to the standard deviation from the mean. So in this case, the individual is what? 2.3 points below the mean. And how you can do that is you can take the individual value minus the mean, and then compare that to a typical deviation. So in this case, the individual had a score of 4. The average was 6.3. And there you can see that the individual is negative 2.3 or 2.3 points below the mean. Okay. Now compare that to a typical deviation, which is 2.6. And that would give you a z-score of, let me go ahead and do that, 2.3. It's actually negative 2.3. Divide that by a typical deviation of the standard deviation, 2.6, negative 0.88. Negative 0.88 is where this individual would be negative 0. On the standard normal curve. And then you could use the standard normal table. You can Google standard normal table, find that individual deviation, negative 0.88, and that would give you the percent to the left. That's what standard normal tables do, is they give you those percentiles to the left. A percentile is the percent to the left. So that would be good. You know, if we wanted to, we could convert that over to a standard normal so that we could compare that to other normal distributions and get a corresponding percentile using that z-score. That would be great. Another thing that we could do is we could use StatCrunch, and if we get to StatCrunch, we could just use not the standard normal, because the standard normal has a mean of 0 and a standard deviation of 1, but if we go to StatCrunch, we go to Stat, Calculators, go down to the normal calculator, so that's Stat, Calculators, Normal, and then just put in your, you can see the default is the standard normal, but just put in your mean. In this case, the mean was 6.3. The standard deviation was 2.6. Make sure that your inequality is oriented the right way. They want the probability that it's less than 4. And then that gives you the probability, about a 19% or 0.188 probability that an individual will have a score that's less than 4. They want to 4 decimal places, so we can cut and paste that to 4 decimal places. That needs to be rounded up to a 2, but that's okay, I can remember that. Round that to a 2, and then that should do it. Find the probability that it's between 4 and 6. StatCrunch can help you with that as well. Hit between 4 and 6, and that will give you the probability. I'm guessing, again, it's 4 decimal places. I need to round that appropriately. So I need to round this up to a 9 when I paste it in. Find the probability that it is more than 8. So that's to the right, right? Greater than, more than 8. So let's do that. Back to standard, make sure it's more than or greater than 8. 4 decimal places. I think that is rounded appropriately. All right, so you can see there that the standard normal, right? The standard normal can take a normal distribution and convert it into something that will help you compare it to other normal distributions if necessary, right? So this tells us that z-score takes the individual value, our first individual value was 4, and it tells us how far away it is on the standard normal. It says that it's 0.88 standard deviations below the average. That's a standardization, kind of like when you get a test score. If you score a 4 out of 5, you standardize it and say that's 80%. Same thing, you standardize normal distributions with the standard normal, which helps, right? But if you want probabilities, there's also ways, and the standard normal can give you a probability to the left if you use the standard normal table. I didn't do that in this video, but you can get the standard normal table and get the percent to the left. But you could also use the normal calculator in StatCrunch. I showed you how to do that in this video. The last part of this problem says, is there any unusual events? And anything unusual, I think what they say is that unusual events have a probability of occurring that's less than a 5% probability. The probability that somebody has a response less than 4, let's kind of convert that over to percents in our head. It's like a 19% probability. That's not unusual. What's unusual is anything less than a 5% probability. 26, closer to 27% probability, that's not unusual. 26% probability is not unusual. Anything that has a probability of happening that's less than 5%, or as a decimal, 0.05, that will be unusual. There's nothing that's unusual here. There are no unusual events because all the probabilities are greater than 0.05 or 5%. All right, so that gives you a good orientation to a normal distribution and how we can create probability distributions from that. We can convert over to a standard normal if we need to. So if they just give us a z-score, if they don't give us an individual value, what if they just give us a z-score? Well, what that does is that clues me off that we're talking about the standard normal. Standard normal has z-scores that correspond to a mean of 0 and a standard deviation of 1. And then we also talked about how we can use StatCrunch to use the normal calculator. Okay, hope that helps. Talk to you next time.